it's feeling recharged. Now let's dive into today's discussion. First of all, I want to welcome Dr. Sevgi to the stage to share his valuable insights on from engineering electromagnetics to electromagnetic engineering. With his extensive experience in electromagnetic theory, modeling, and engineering education, we are excited to hear his perspective on shaping the future of this critical field. Please join me in welcoming to Dr. Sevgi to the stage.
We'll start this slideshow. Okay, good afternoon. The title of my presentation is Transformation from Engineering Electromagnetics. It used to be the title of the lecture when I was a student, undergrad student, more than 40 years ago, and to electromagnetic engineering. And this is the outline. I'm going to show you a few slides, first about electromagnetic engineering, then we will see revisit electromagnetic theory, Maxwell's equation, and challenging current problems. And the second part, if we have time, is about modeling and simulation in electromagnetics. And if you do numerical simulation, modeling and theoretical modeling and numerical simulation, you need to calibrate your software, your simulators. So validation, verification, and calibration, VVNC, is critical. And we will end up with the conclusions and discussions. Let me show you a few slides about myself. First, I spent 40 plus years dealing with electromagnetics. And I was with 4 different universities. Istanbul Technical University. This one is the oldest university in Istanbul, more than 250 years old. The other 3, Dogus, Okan, and Atlas, are relatively new foundation universities. We don't have private universities. We have state universities and foundation universities. I did my PhD in New York Polytechnic. And I spent 2 years with Raytheon Canada during my first sabbatical term, and another 2 years in UMass Lowell. I was the chair of TÜBİTAK, which is a national research center, for 2 years, and spent also more than 30 years in military projects, defense projects. And I'm an active IEEE volunteer, and in the last 5 years, very active with the APS also. These are the outcome of my 40-year studies, lots of journal transaction papers, scientific conference, 20 plus keynotes, opening speeches. I have visited and still visiting 100 plus universities. I have chaired and co-chaired international conferences. And since the beginning of last year, we have organized 13 inter-society distinguished lecture workshops. So this is the 13th one. And these are the critical subtopics I have studied with the last 40 years: radiation, antennas, scattering, electromagnetic wave object interaction, electromagnetic compatibility, diffraction, measurements, circuits and systems, sensors, and propagation. And if you deal with those topics, you need to well understand and well apply data processing, stochastic modeling, and integrated system designs. We teach all these topics in a deterministic way, especially for undergrad lectures. But life is stochastic. So nothing is stationary, nothing is linear, nothing is homogeneous. Nothing is stationary in real life. These are the books I have published. That one is the first one. The red one is my favorite one that I published while I was in UMass Lowell. The most recent ones was the left one is about propagation, parabolic equation modeling of radio wave propagation. The most recent one is diffraction modeling and simulation. And this is still under preparation. Hugo will be my co-author. He's a handsome Spanish professor in Griffith University, Australia. We are still late, but working on this one. Probably that will be the last one. I was lucky because I have met excellent people while studying with electromagnetics. Ercan Topuz was my first advisor in Istanbul Technical University. He's emeritus now. I was a PhD student of late Professor Leopold Felsen. He was giant in electromagnetics, and we have collaborated. We had collaborated with him more than 20 years. And after he passed away, his son, according to his will, his son has been sending us $5,000 every year for successful students, Turkish students in Turkey. So Mehmet was one of the recipients in 2013. Also, this is another professor, Turkish professor. He was the director of NATO defense studies in Europe. He was the director of first NATO satellite from Europe. And we spent more than 20 years together with him for Turkish defense projects. This guy, Ufimtsev, is a Russian-American. He is the mathematical founder of PTD, Physical Theory of Diffraction. We have been collaborating with him, especially in modeling diffraction, electromagnetic diffraction, since 2011. Also, this is a Greek-American professor, Balanis, from similar culture. Turkey and Greek are similar cultures. And last but not least, Rai Mitra, MTT professor. We also have joint studies with him. I have visited more than 70 countries in the last 30 years. And maybe 30 of them, half of them, are after I became IEEE AP Distinguished Lecturer. These are some of the logos, maybe 20% or less of the universities I have visited with. And I was the editor and founding writer of this column, Testing Ourselves. It was a column in the Antennas and Propagation magazine. And we created this column with Roston. He was the editor-in-chief at that time. We published more than 75 tutorials in 14 years. And some of the tutorials are very basic, like reciprocity, what is an antenna? Still, we don't know what antenna is. Biostatics, RCS, signal, noise, and clutter generation, synthetic generation of those. And some of them were highly comprehensive. And we have prepared and published and shared with the IEEE members what we call them electromagnetic virtual tools. And these tools have been in use in different universities from United States to China for years in different universities. So if you want to teach electromagnetics, propagation, diffraction, antenna, beamforming, scattering, and others by using these virtual tools, because you can visualize electromagnetic waves with these virtual tools, then go back and deal with Maxwell's equations, the theory. Okay, that's the introduction that I have been doing in the last 40 plus years. Let's start with the electromagnetic engineering. So we are engineers. We deal with physics, which means the real life. Physics, I mean the real life. Mathematics is a wonderful tool. We use mathematics, and we speed up with the computer. So computer is a stupid box, but it's very fast and it never gets bored. So we speed up with that one. So there is an interrelation between the real world, conceptual world, and synthetic world. And this necessitates to establish an intelligent balance among mathematical background, engineering experience, and numerical simulations. So you have to train your students strong in terms of theory, practice, and numerical simulations. So instead of calling microwave engineering, radar, antenna, very large-scale integrated systems engineering, communication, biomedical, EMC, today we prefer to call it electromagnetic engineering. And this is the reason, because the role of electromagnetic waves in our lives has changed in the last 30 plus years. And when I first met with electromagnetic lecture, it used to be engineering electromagnetics. And if you are lucky, you see one airport antenna, if you're living close to airport, and one maybe long wave radio transmitter tower. But today we carry electromagnetic devices on us, cell phones, Bluetooth devices, everything. So we have systems from communication to defense, and the frequencies vary from DC to terahertz, even above. And the sizes of the systems that we are using vary from nanometers, 10 to the power minus 9 meter to kilometers wide. So if you want to inject an antenna in your blood, then it has to be small enough. But if you want to communicate with your frigate a few thousand kilometers away from your country over the ocean, you need a kilometer or 2 kilometers wide antenna systems on the shore. And almost all of these systems are broadband and digital today. So that's why we prefer to call electromagnetic engineering instead of all these subtitles. And these are topics under electromagnetic engineering: propagation, antenna design, RCS and stealth technology, low visible target design, 4G, 5G, new materials, artificial materials, non-physical materials, biomedical engineering, subsurface tomography, and they are interrelated. For example, if you want to show or deal with a multi-sensor integrated system, I'm going to show you a few slides as an example. You need to well understand all these subtopics. Let's see one example. For example, if you want to design conceptually and then practically a multi-sensor surveillance system, suppose you are the Prime Minister of Italy, the country may be anything, United States, Turkey, any other country. And if you want to observe all surface and air activity around your country continuously under all weather conditions, and you need to design a multi-sensor surveillance system. So what type of sensors are you going to use? For example, are you going to put an HF radar over there with that coverage area? And is it the best location? Or how many additional sensors, HF radars, with what coverage, cross coverage and range coverage are you going to design? Are you going to use microwave radars, microwave sensors? Are you going to use sensors on the airplanes? And microwaves, we know 8 to 12 gigahertz. HF is 3 to 10 megahertz. The frequencies, the wavelengths are totally different. And all these sensors will going to send you data continuously. So you need an operational control center to receive and to process all these data. So if your mission is to detect and track every target around your country, this is a concept. And the conceptual design of such system may take several years. And you need to well understand all physical challenges there. For such system, you need to well understand how electromagnetic waves propagate in different frequencies under different geographic conditions. Sea clutter, for example, if you want to detect ships on the ocean or on the sea, you send signals and receive backscatter from the ships, but you also receive signals from the sea waves. So sea clutter, electromagnetic wave, ocean interaction is also critical because we have calm sea and we have windy and we have thunderstorms. So sea states is a parameter which we use from calm sea to disaster sea conditions. So nothing is linear in terms of electromagnetic wave, ocean wave interaction. So you need to well understand physics of that interaction. Ionosphere is also a terrible environment if you are using such integrated surveillance system because your signal propagates through ground waves, also ionospheric reflections. And ionosphere is a cloud of electrons. And the density of the electrons change from day to nighttime, from season to season, and even through the sun cycle of 10 to 12 years, because sun is quiet at some years. In some years, sun becomes very active with magnetic storms. So you need to well understand all these issues. Noise, you need to survive under noisy conditions. Antenna design, digital beam synthesis and interpolation, frequency crowded bands, target RCS, radar cross-section. And among all these, you need to well understand and apply signal processing, detection, tracking, classification, identification algorithms, as well as threat evaluation algorithms if it's a defense project. So multi-sensors, data fusion, multi-sensors, sensor fusion are also challenges. We designed such system in North America and Canada, in this region, Atlantic Ocean. That's 300 kilometers away from Newfoundland in Canada. And that region is very rich in terms of oil reserves. And Canada uses these oil platforms to get the oil, underwater oil from there. And the enemy of the Canada, that system, is the icebergs coming from north because of the global warming. And huge icebergs may hit those oil platforms and destroy the platforms. And the economy of the Canada, the country, may be in danger for several years. So they use that system, integrated surveillance system, to detect icebergs. But different countries may use such systems for different purposes. For example, Turkey will use such system in Mediterranean Sea to detect Greek frigates. Israel uses such system to detect missiles. So the mission, the problem may be different, but the solution approach, the challenges are similar. For example, this is a real-time data, this video, and you have dots showing ships over there. Are they really real targets or computer-generated noise or ghost targets? How do you evaluate? How do you test such systems? So that's one target over there. And this is the detection picture in order to say that there is a frigate, there is a ship over there. So this picture shows you the frequency on the horizontal scale and range over the scale. So that ship is just one point in that clutter and noise generated real spectrum. So how are you going to detect one small ship in this scenario. So you need to well understand the physics of the problem, then develop and use detection, classification, and tracking algorithms. So this is what we teach for undergraduate lectures. So you have signal, the received signal, the power of the received signal in the vertical direction. The horizontal direction may be time, different distance, or frequency. It doesn't matter. So you have signals, noise, and everything over there, and you set up a threshold for a given signal to noise ratio, and you then said, okay, anything above the threshold is target, below is noise. So that's the digital form of that one. So this is a theoretical or sample example that we show for the students. But in the real life, so this is the data, what we get. So this is the noise floor, and that's the constant false alarm rate threshold. And that is the test ship we used, and that's the location of that ship in this picture. So it's not easy to detect and track targets under very high clutter and noise environments. So it comes to well understanding the physics, the real life, better understanding of these activities. So those high peaks belong to C waves, which resonates with the radar signals, so which we call Bragg echoes. So if you know the physics, you can get rid of them. Otherwise, you treat them as targets. So for those examples, these are the critical keywords: radiation, which is related to antennas; propagation. After you radiate, you generate electromagnetic waves. It propagates through physical environments. Then it interacts with objects. So anything belong to that interaction is called scattering, electromagnetic scattering. And the critical part of scattering is diffraction, because I will show you another slide. So for the radiation, that's the line source, vertical dipole, horizontal dipole. These are beams generated. So antenna array, its calibration are critical under electromagnetic energy. And this is one virtual tool that we developed more than 25 years ago. So this is one front panel virtual tool. We give this to students to generate different arrays, planar arrays, circular arrays, and then beam forming and beam steering capabilities, and then go to classroom and teach mathematics behind this one. And this belongs to this virtual tool. If you deal with antenna, usually communication people deals with antenna in terms of beams formed and antenna gain. But if you are an EMC engineer working in a lab, anechoic chamber, you need to well understand how you calibrate the antenna. That's the critical part of the antenna. So here, on the transmitters, we generate voltage, use current, and then it generates electric field, electromagnetic field. Then on the receiver side, we change it to voltage again. And this transformation from V to E and from E to V is directly depend on the calibration of the antenna. And usually we need to measure that one. So that is called antenna factor. If it's on the transmit side, tough transmit antenna factor. If it's on the receive side, it's called antenna factor only. So E over V is the critical parameter for EMC engineers. But communication engineers, they don't deal with such kind of calibration issues, antenna calibration. If you are a propagation engineer, and if you want to cover, for example, such a rural environment, for 4G, 5G applications, how many base station antennas are you going to locate on this given digital map? So these are scattering effects, these are the applications, and these are the physical effects that change the scenario of the propagation. So if you use more base station antenna, it will cost you more. If you use less, it will give you less performance. So you need to find optimum number of base station antennas for a given digital map, for a given area. This is another virtual tool which we use for propagation, two-dimensional range versus height. You put number of, use mouse and number of points and generate with interpolation of those points, generate non-flat terrain profile and locate beam antenna and beam steer downwards, upwards, and then see how electromagnetic waves propagate. For example, this video shows you electromagnetic wave propagating through a two-dimensional scenario under different non-homogeneous atmospheric conditions. So although you send electromagnetic waves down to surface, it may never reach the surface and create a kind of elevated duct because of the atmospheric change. So that is the reason sometimes you can listen FM radio while you are driving in the morning in your car. Some stations may be heard good, sometimes bad, because of the atmospheric conditions. So atmospheric conditions are critical in establishing radio links between 2 points. If you are a radar engineer, sensor engineer, your mission is to detect target as early as possible. But if you are an aircraft engineer, you want to hide your aircraft as much as possible. It doesn't matter whether you are a radar engineer or aircraft engineer, you need to well understand electromagnetic scattering and diffraction theories. These are different electromagnetic effects around this fighter. We have tip diffractions, we have edge diffractions, specular reflections, traveling waves, echoes returns from engine cavities. They act like resonators. So in time domain, we call it ringing effects. In the frequency domain, we call it resonance effects. So you need to well understand all these electromagnetic effects, physics behind these effects in order to deal with them, in order to use them, or in order to protect yourself from them. And this is a history. As I told you, we have been collaborating with this guy. He is the father of PTD. And this is the history of low visibility stealth aircraft. So Lockheed was the first design F-117 Nighthawk. And it was first used in 1991. Then it was first shut down in 1999 because if you know the physics, you can design very low visible targets. But if you know the physics, you can capture very low visible targets also. And low visibility is effective, especially for microwaves and above, because all the targets are designed against microwave sensors. But HF radars, both surface and skywave HF radars from 3 megahertz to 30 megahertz have the capability to detect them. I'm going to show you a few examples. Also, VHF radars VHF signals can go behind the heels, behind the targets because of the frequency region. This is another virtual tool which we designed to understand scattering and diffraction effects. It uses two different methods, method of moments in the frequency domain and FDDT, finite difference time domain method. And all you need is to choose your target. For example, here, the DC10. If you give me B, this is the graphics file of that target in any format. Here we use 3ds format. Our virtual tool automatically creates FTDT discrete model and method of moment discrete model of that object. And then it runs and gives you scattering in the time domain. So you send a plane wave here, but it's a pulse in the nature. So it hits the object, scatters, you put number of receivers all around the object. This is only a few picosecond scenario. So it gives you transient effects. You record them, do Fourier transform, and get the RCS, because RCS is defined in the frequency domain. Most of the parameters that we know, RCS, impedance, they are all in the frequency domain. So you can easily get the RCS in the frequency domain. And this is the result. So on A, side illumination, on B, oblique illumination, and the frequencies are different, low frequency, high frequency. The most important information here is this forward scattered component. You see, you have always strong forward scattered components. That's the limit of low visibility, stealth design. If you focus on this forward scattered, what we call shadow radiation also, you can easily detect those objects. Let me show you these videos. So we have a perfectly electrical conductor strip, infinite in this direction. So we show scattering effect in this cross section. On the left, total fields. So you send plane wave, it hits the object, and it generates reflections, strong reflections. So they interfere here, but behind the object, you have a shadow region. If you subtract incident field from that one total field, you get scattered fields. So you send the incident field, and it scatters. If you remove the incident field, you focus on the scattered fields. This shows you scattered fields. So strong specular reflections, strong forward reflections. If you add incident field to this one, incident field behind the object and forward scattered fields have opposite signs. They cancel each other and they give you shadow radiation behind object as the frequency increases. If you change the angle of illumination, again, total fields on the left, scattered fields here. You see strong forward scatter and specular reflection. And again, shadow radiation behind the object. And you see the interference of the incident field and reflected field here in this region. And the most limiting case is the edge illumination, total fields. If you subtract the incident field, you end up this one. But here we have soft hard boundary conditions. So the boundary condition here and here on this side are different. Soft and hard boundary is used in acoustic society. In electromagnetic society, we name them transverse electric and transverse magnetic boundary conditions. Mathematics society uses Dirichlet and Newman type boundary conditions. They all refer the same. So you have a strong surface waves, nothing on the other side. So visualization is very important in understanding, observing, and identifying different electromagnetic effects. So in summary, we have total fields with the addition of incident and scattered fields. So mathematically, we can write a total is equal to I incident and scattered fields. And scattered fields has the components of reflections, diffractions, if it's a penetrable object, and diffractions. We also have some other critical issues like surface waves, traveling waves, but usually these three. So if you subtract the incident field, you can focus on the scattered field and observe it. And again, if you can subtract incident and refracted fields, you can observe focus on diffracted fields. Mathematically, we can separate this. We have been using high-frequency asymptotics like geometric optics, geometric theory of diffraction, GTD, physical optics, PTD. But can we do the same numerically? With the collaboration of that Russian professor, we have been doing this in the last 15 years and published more than 30 papers about diffraction, numerical modeling of diffraction theories. So if you have a sharp object, if you have a line source, this is the line of sight which separates interference region with the shadow region. No incident field here, you have incident and all others there. So if you have a base station over there, if you stay here with your cell phone, you can establish the communication between your nearby base station only by means of diffraction, diffracted terms. So usually we don't see the base station around. So here we can use our cell phones, right? That's the diffracted fields which establish link between our cell phone and nearby base station antenna. And the colors of the signals shows the amplitude of the signals. So if you have incident and reflected fields, you don't need to worry about diffractions because it's 1 or 2 orders less than this one. But usually we don't have incident field, line of sight, and we don't have reflections, only we have diffractions. So you need to well understand how diffraction occurs in different problems. This is a diffraction problem from a wedge type scenario. There's a pulse line source. You send it, it hits the wedge tip, and you observe time domain pulse propagating from a line source. So you see, it comes, this is the face front of the incident field. So we have reflections, this one, and also you observe light color with diffractions fall around the object. If you capture incident fields, screen capture during the time domain, that's the incident field. This is the reflection. This is the reflection at a later time instant, and this is the diffracted fields. So any edge, this is the edge of an object, and this is the tip of an object. So the sharp edges and tips cause diffraction, and they act as secondary sources. They generate and re-radiate secondary sources. So if you can do simulation by knowing the physics, first you run the wedge scenario, then you replace it with infinite plane wave, and then you remove it and free space. And in each case, we have some of them we have diffractions, some of them we don't have diffractions. So for the wedge problem, we have everything diffractions because we have tips. But in the second scenario, we have only incident and reflected fields. Here, only incident and reflected fields. So you can subtract one from other, as we have been doing with the high-frequency asymptotics in mathematics. You can easily distinguish reflections, diffractions, scattering, and other components, as you have been observing in these slides. So that's the critical angle of incidence. That's the critical angle of reflections. And if you can put number of receivers around the wedge, and then get these kinds of simulation results. This is the total field around the wedge. Total field around the wedge. So you have here the interference of incident, reflected, and tip diffracted waves. Here only the incident field and diffracted fields. Here in this region only diffracted fields. If you subtract the incident field and the reflected field, you end up diffracted only fields. So diffraction accumulates along two critical angles, angle of illumination and angle of reflection. So you need to well understand physics, those physical terms, in order to design all your systems. It doesn't matter you are MTT society guy, GRSS guy, aerospace electronic systems guy. You need to well understand electromagnetics first. How much time do I have? 20 minutes. Okay, good. This slide shows you line source in two-dimensional space with, this is refractive index, positive. This is a positive material. If the refractive index is negative in all these three, it means epsilon R and mu R are negative. So these are metamaterials. This is regular material. Line source generates electromagnetic waves, cylindrical waves. It propagates through positive wave, but you see how it propagates through metamaterials. So here, inside the metamaterial, the wave seems to go in the reverse direction, right? That's the phase of the wave. Actually, because of the power conservation, because of the Poynting vector, energy always propagates in the forward direction. It doesn't matter if it's a metamaterial or not. Other types of metamaterials. So we are lucky because electrodynamic theory, Maxwell's equations can handle non-physical, non-natural materials also. And these metamaterials have been used in lens applications, antenna applications, especially to minimize the dimensions in the last 10 or 15 years. So we have another metamaterial slab here, air, and we send a beam type of energy, and these arrows shows the Poynting vector. What we know from the Snell's law, if as a ray comes here, the angle of this one and the angle of refracted field are on the same side of the normal, right? But here, you see in the negative. So we have negative Snell's law. It goes here. If it's a positive material, it should go this way and then this way. But it goes in the reverse direction. So you can change the direction of beams by using metamaterials, artificial materials. Okay, for all these applications, we are lucky because we have electromagnetic theory well established with Maxwell's equations 150 years ago. You see, there is an emergency button there. So if any of you say that, okay, I'm sick of electromagnetics, then just let me know. Or if my time is up, then let me know. Just press that button and then jump to conclusions, okay? Don't worry. Okay, these are the Maxwell's equations. On the left, you see them in differential form. On the right, in integral form. And circuit theory, people doesn't like this. But we don't have circuit theory. It's a subset of electromagnetic theory. Don't tell this in front of circuit society people. They don't like it. But this is the fact. When I was an undergrad, I used to hate electromagnetics because of all these symbols, because it's pure mathematics. I was successful. I get good grades, and then I passed the class. But at that time, our professors didn't tell us the physics behind mathematics. Actually, now I love these equations. But 40 years ago, I hate them. I used to hate them. Because differentiation is nothing but subtraction, okay? You subtract two things. And integration is nothing but addition, just accumulate. So differentiate, subtract, and add. So just give me the sources. We have two types of sources, charge density and also current density. These are the two who generate all kinds of electromagnetic waves. And any kind of material object, environment, even human tissues can be modeled with sigma, conductivity, mu, and epsilon. If you give me epsilon, mu, and sigma of anybody, any person, any environment, I can give you electric and magnetic fields, electromagnetic fields everywhere by using those two simple equations, Maxwell's equations. So that's the beauty of electrodynamic theory. But we are lucky because even, as I showed you before, even non-natural objects like metamaterials, we can use them. They are still valid. So Maxwell's equations are general. It can give you solutions of antenna problems, scattering, diffraction, propagation. Once you state your boundary conditions, which means once you introduce your geometry, it will give you only your solutions. And from electrodynamic solution theory, we know that the solution exists. And if you can find it, it's the unique solution. So mathematically, it is proven that Maxwell's equations satisfies existence theory and uniqueness theory. If you are lucky, you have analytical exact solutions, but we have only a limited number of highly simplified, highly idealized geometries with exact solutions. And usually they are in the form of infinite series summation or infinite integral, complex integral. So their numerical solution is a challenge. But we can use high-frequency asymptotics, like I said, GO, GTD, PO, PTD. And high-frequency asymptotic means the frequency is very high, so the wavelength goes to zero, almost zero. So any object, the dimension of any object is very huge compared to wavelength. So I can use localization. I can focus on this part only or this part wherever I want. So that's why we call this high-frequency asymptotics. And we are lucky in the last 3 decades because we have fast and high-capacity computers. So we have numerical simulations. Still, we have discretization problem. Time and memory allocation are also a challenge. These are high-frequency asymptotics. The first 3 of them are called ray-based models. So you assume electromagnetic waves as rays. GEO gives you only reflection and refraction. Diffraction, GEO cannot take into account. So they introduce GTD, geometrical theory of diffraction. GTD suffers from critical angles. Remember, I showed you angle of incidence and angle of reflection. So GTD fails during those critical angles. So UTD was introduced, but UTD still suffers in caustics, where electromagnetic rays cross-section comes to zero. The second approach is Ufimtsev, that Russian professor's theory. We call it physics optics and PTD. They are current-based models, but these currents are source-induced currents. So if you have a transmitter here, you send the incident field, it interacts with any object, airplane or anything, and it creates surface currents. It generates surface currents. So those are source-induced surface currents. If it's an penetrable object, you also have body currents. So if you can find those currents, you just use radiation integral. That's one simple integral, and get a field around the object anywhere you want. And these are all famous numerical models, FTDT, TLM. Those two are in time domain. Method of moments is the first one, the oldest one. In the frequency domain, parabolic equation is very suitable for propagation modeling. Also, we have finite element modeling. Whatever your problem is, they can be grouped into 3, roughly speaking. We have antenna radiation problems, RCS and scattering problems, and guided wave problems. And in each of them, we start with the same one. Maxwell's equations and give your boundary conditions. But use different routes. For antennas, we use auxiliary scalar and vector potential functions because they are in parallel with the sources, with the currents. Then we derive electric and magnetic fields. For RCS, we know the incident field, that's our signal. We remove it, we focus on the scattered field. And for guided wave propagation problem, we have cables, we have transmission lines, we have waveguides. So we can guide electromagnetic waves. So there we start with Maxwell's equations boundary condition, but decompose Maxwell's equations into two parts, transverse and longitudinal part. The transverse part will give you eigenvalue problem in mathematical theory. The longitudinal part will give you Green's function problem. If you hear Green's function, this means you have a source. And the most limiting source, non-physical source, is the point source. That's not physical, that's mathematical source. In 2 dimensions, we have line source. That's not physical. It's not possible to generate in real life point source or line source. We can approach, but not one. So line source in 2-dimensional or point source in 3-dimensional with Maxwell's equations is called Green's function problem. And I was the chair of Mediterranean Microwave Symposium in 2012 in Istanbul. I invited Ufim Sev to talk about PTD. I also invited this Greek professor, Balanis. Maybe you know him from his antenna books. They are both above 80 years old now. And he talked about GTD. I wanted them to fight with each other because they are both Orthodox. One is Greek, the other one is Russian. But they don't like each other. But they enjoy each other very much after a couple of Greek Uzo and Turkish Rakı, gala dinner. Then we published this 50 years of high-frequency diffraction, which is Balanis' contribution on GeoGTD, Ufim Sev's contribution on POPTD, and my contribution with the modeling and simulation side. Okay, the second part is modeling and simulation.
You have around 5 to 6 minutes.
Okay, so just let me show you a few slides and then we skip to conclusions. So there are different types of simulations, task trainer, virtual reality, you can use many kind, and physics-based simulations. What we are talking here is this one, physics-based simulation. So this is the definition. So use computer numerical simulation based on physical understanding, mathematical conceptual visualization, representation of any real-life problem, device, or system. So when do we need simulation? Sometimes it's expensive and time-consuming, sometimes dangerous. Sometimes it is impossible to do tests with real systems. And very often, maybe more than 90%, we don't have the real system. That's why we want to simulate it. And the most beautiful part is, once you calibrate your simulator, you can play what-if type games. What if I change the frequency? What if I change the material properties? It's like a lab, free lab for you. So this is the generic picture: physics, mathematics, and your code. You do sometimes numerical analysis, root search, interpolation, extrapolation, optimization. You can design a graphical user interface, and then you get the result. And we call this EM package, or we prefer this one, electromagnetic virtual tool. And you directly start with the Maxwell's equation, do the discretization without boundary condition, and then get your virtual tool. So anybody who uses this one can introduce his or her boundary conditions and solve this problem. All those numerical methods, FDTT, method of moment, finite element, parabolic equation, they are either closed form or open form approaches. For example, method of moment is a closed form representation, as I said to you before. You send an incident field, it generates surface currents. So the currents is variable all around the surface. If you divide it into small parts, that each part, the current, source-induced current is assumed constant, then instead of dealing with integration, you can solve it with systems of equations. But that's why we call it closed form representations. So you divide this into, let's say, 1 million pieces. So you have 1 million unknowns, which means 1 million, you need 1 million equations. So if you can write 1 million equation with 1 million unknowns, the rest is matrix inversion and solution. Always stable, but huge matrices and contractions problem. Open form representation. So we have two Maxwell's equations, right, in vector form. So in X, Y, Z space, if you write scalar form, you have 3 from 1, 3 in the second one, so 6-line scalar equations. So this requires, for example, FTDT requires only 6-line MATLAB codes. If you discretize Maxwell's equations in the 3-dimensional space from the beginning, you only need just 6-line MATLAB codes. It's very simple, but stability is a problem. You have to watch out the problem. Boundary conditions is problem. So for 6-line full wave Maxwell's equations FTDT form, you need to write maybe 1,000 additional lines to satisfy the boundary conditions, or another 500 line codes for another source implementation, etc. But closed form versus open form. And you need to be very careful because you introduce assumptions, you do approximations, simplifications, and at the end, discretization. We call analog word on them, and discretization belongs to synthetic word. So you have to be careful. You need validation, verification, and calibration. And these are the definitions of validation. Validation asks whether the right model is chosen or not. So you have different models, you choose one of them. Does that one represents your problem? That's the issue of validation. Then you write your code. Verification asks the question whether you built the model in the right way. And calibration is nothing but testing the result with the reference data. But very often we don't have reference data. So we have to assume something as reference. For example, we have met hundreds of cases. We compare method of moments against FTDT. We compare FTDT against TLM. We compare high-frequency asymptotics with method of moments. Sometimes they agree very well, but they both are incorrect. Because if you do the same mistakes in both of them, you get agreement, but non-physical or non-true solutions. So you have to be very careful. And this is the last picture I want to show. Real world, with what we call physics, you choose one conceptual model, one set of equations. You do conceptual validity through physics-based analytical modeling. Once you are sure that this set of mathematical equations represent your problem, you write a computer code. For the same equation, 20 people may write 20 different codes. So you need code verification. We call it computer programming. At the end, you get a number from the computer, and you need operational validity. You need to test it against reference. Very often, we call it numerical and physical experimentation. We are engineers. At the end, physical experimentation is a must for us. So let's push the panic button. And now the conclusions. Okay. Electromagnetics is everywhere, so you have to well understand physics. You need modeling and simulation and VVNC type lectures or teaching, training. First, physics comes first, then mathematics, then simulations. Always keep in mind the assumptions and validity ranges, and always look at the object as a whole, but pay attention every details. So if you are a regular professor like myself, you just treat it as a whole. If you are a professor who pays attention to details, you can win Nobel Prize. So the critical information is hidden under details. Always remember that. And multiphysics has become essential. So electrodynamics, thermodynamics, and mechanical engineering and chemical engineering, we have to work together. We have artificial intelligence, but hands-on training is a must in our area. And unfortunately, we remove basic lectures like measurement techniques. We strongly need them because we need to do error analysis, uncertainty analysis. I know professors who doesn't know anything about error and uncertainty analysis. Teaching training, these virtual tools have different outcome. Sometimes we were very successful in some classrooms, but sometimes we fail because it depends on the nature of the students. If they are willing to play with simulators as well as with mathematical derivations, then the classroom is successful. If not, it's not easy. But it establishes understanding physics, math, by using the visualization of electromagnetic waves. And today's electromagnetic engineering students are very lucky because there are excellent commercial packages and measurement devices. You just press the buttons for both of them. But they are also very unlucky because there are excellent commercial packages and measurement devices. It's up to you who is going to be the boss. If you are the boss, you can control both of them, then you're lucky. If they are the boss, you just look at and push the buttons, you will be in trouble. This is the motto I used in my first book, Let's Do It. This is the motto in my second book, Yes, You Can. I borrow it from Obama. I didn't steal it, just borrow it. And this is the motto of the IEEE. Tell me, I'll forget. Show me, I'll remember. Involve me, I'll understand. And that's the end of my presentation. Thank you.
So we can take some questions.
Yes, please.
You were talking about the Maxwell's equations and EM wave model. So we have seen from NVIDIA's ray tracing that they can mimic the real world optical electromagnetic interactions with ray-based models quite realistically. So when does this ray-based model breaks down? Like what are the boundary conditions where we need the wave theory instead of considering the ray theory?
As long as you satisfy the fundamentals of ray, the definition of the ray, it can work from very low frequency up to optical, even above. Rays are straight lines in homogeneous world with infinitely small cross-section. So we assume zero cross-section, but they carry finite energy. So if you want your rays be more physical, you use ray tubes, okay?
Okay.
So the cross-section of the ray is proportional with the energy of the ray, the power of the ray. So it is not the frequency range where your rays may be successful or may fail. It is the definition of the rays. In some scenario, the cross-section of the ray goes to zero because the ray tube may go this way, in usual way, diverge, but in some cases converge because of the non-homogeneous nature of the environment. Okay, if it converges to zero, we call it caustics. So in caustics, rays fail So you need to treat electromagnetic energy as waves instead of rays. Okay. So you can use rays wherever you want, as long as you stick with the definition of the ray, okay, the fundamentals of the ray.